All right. Last time we talked about conditional probability, Bayes' rule, and the total probability theorem, and we solved a number of interesting problems. Today's new topic is independence, but we'll start by solving the problems we left out from last time. Remember, if you go back to the end of last lecture, we had two problems. The first one is about the detection of an aircraft, and the second one is about, maybe let's turn the screen, these lecture notes off for a while and work out these problems. The first one is about detecting an aircraft by a radar. Okay? So, okay, here's the problem. Let's call it example 1. Okay, I'll read the problem statement, but you should also have it in your handouts. If an aircraft is present in a certain area, a radar detects it and generates an alarm signal with probability 0.99. Okay? If an aircraft is not present, the radar detects a false alarm with probability 0.1. Okay? We assume that in the presence of any information from the radar, an aircraft is present with probability 0.05. Okay? The question is, well, there are several questions. What is the probability that there's an aircraft and the radar detects it? What is the probability that there is an airplane given that the radar gives an alarm? Okay? So we will use the language of conditional probability, and we will use Bayes' rule to answer these questions. So let's see. Okay, so let's begin by making some definitions. So let A be the event that an airplane is flying above. We're given that P of A, the probability of A, is 0.05. This is the prior probability of A, okay, in the absence of further information. Event B is defined as something registers on the radar screen. So radar gives an alarm. Okay? The probability of this, is it given in the problem? No. We're supposed to compute it. Let's see if we know enough to compute this probability. Let's start by answering part A. Part A asks us to find the probability of A intersection B. This is the probability that there is an airplane in the sky and the radar detects it. Okay, how do we find this? Well, use the definition of conditional probability. Okay, we can break this up into the product probability of A, probability of B given A, right? Okay. Probability of A is given as 0.05. The probability of B given A, is it given? Let's see. What is it? 0.99, right. This is the detection probability, and it's quite high, 0.99. Okay, so if you take the product, you get 0.0495. So as expected, this is a little lower than 0.05, which is the probability that there is an airplane in the sky. Okay, let's do part B. what is the probability that the radar generates an alarm, whether or not false alarm, whether it's false alarm or a correct alarm? What is the probability of B? How would you do this? Exactly. Use the total probability theorem by taking the partition A complement. Okay, so the probability of B can be written as the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. Okay, do we know the probability of A? Yes. Then do we know the probability of A complement? Yes, it's 1 minus 0.05, which is 0.95. Okay, so PB given A, 0.99, P of A, 0.05, plus B given A complement. 1 minus? Let's think. That would be B complement given A. Right. This is the probability that the radar gives an alarm given that there is no airplane. Right. This is the false alarm probability specified in the question as 0.1. Times probability of A complement, which is 0.95. And this comes out as 0.1445. Okay? Any questions about this? All right. So let's move on to part C. Okay, the part C is the real question. This is the probability of A given B. In other words, probability that there is an airplane, given that my radar gave an alarm. Okay? Just as in any sensing system, radar systems are not 100% accurate. Okay? There's a false alarm probability. So given that there is an alarm generated, doesn't mean that it's certain that there is a target in presence of the radar. Okay, so let's compute this probability. What do you, Bayes rule, exactly. P B given A times P of A divided by P of B. And by now we know everything in this equation. B given A was already given as 0.99, right? P A was given as 0.05 and PB was computed, excuse me? Okay, as 0.1445. And the result is 0.3425. So 34%. What do you think? Do you think this is too low? This is the probability that there's actually an airplane, given that the radar told us that there is an airplane. Maybe this is low. Why do you think is this, you know, if you look at these numbers, the given numbers, what is causing this probability to be so low? Maybe this number, the actual probability of the airplane, you know, there being an airplane, being small. Okay, how would you improve this probability if you could? By doing something to your radar system or by doing some post-processing, how would you improve this? Maybe if you play with this 0.99, if you increase this, excuse me? Well, I guess that's beyond the control of the system designer, radar designer. So I guess, you know, potentially if you improve this value, 0.99, made it go closer to 1, you could increase this a little bit. There's very little room though. Although, in practice, increasing this also implies increasing the false alarm rate, which is an undesirable phenomenon. Okay, any questions about this? The next question is from the medical field, and it's a very similar problem occurring in a different setting in life. All of us go and have some medical tests, okay, but I guess not a lot of people have given thought to exactly how to interpret the meaning of these tests. And in fact, a survey done by The Economist magazine some years ago revealed that a lot of people who are working in the medical field, like doctors and nurses, had trouble answering this next question correctly. Okay, here's the example. Example 2. It's the false positive puzzle. Let me get a different color. Okay, I'll read you the question. A test for a certain disease is assumed to be correct 95% of the time. Okay? So if a person has a disease, the test results are positive with probability 0.95. Okay? And if the person is not sick, does not have the disease, the test results are negative with probability 0.95. Okay? It's a pretty good test. Okay. Now, this disease is sort of rare. A person randomly drawn from the population has this disease with probability 0.01. Okay. So, here's the question. Given that the person, a randomly selected person from the population, was tested for this disease, and the test result came out positive, what is the probability that the person actually has the disease? Okay, so why would you test a person randomly selected from the population, first of all, even if he or she doesn't have any symptoms? You know, there may be different reasons. This may be a medical trial, or this person may be applying for a job and, you know, is required to undergo this test, etc. So imagine, put yourself in the position of this person. It's a bad disease, you're tested for it, you got a positive result. And the test is correct 95% of the time. What would you think? What do you think is the probability that you have this disease?
Very small. Very small, I think.
Okay, so a lot of people, including those from the medical field, answered that this probability is closer to 95%. It's close to 95%. They said, you know, the person has the disease with probability around 95%. And, you know, let's compute this. Okay, let D be the event that the person has the disease. Let me switch to another marker. Let this be the event that the person tests positive. And let this be the event that the person tests negative. Okay. So what are we given? We are given that the probability that a person randomly selected from the population has this disease 0.01. Okay, this is the prior probability of having the disease prior to taking the test. Okay, now what else are we given? We are given that the test is correct with probability 0.95. How would you express this? D, excuse me? Positive given D, right? Probability of testing positive given D is 0.95. Any questions about this? Okay. What else? Probability of testing negative given
D complement.
exactly D complement is again 0.95. Okay, so these are the givens of the problem. Now what are we asked to compute? We're asked to compute P positive given, no, P D given positive, right? We need to compute this. Again, let's apply our Bayesian thinking to this. We can write this as, switch the events around using Bayes rule. Positive given D times P of D divided by the probability of positive. Okay, there's something new that we need to compute then. The probability of testing positive. How will we compute the probability of testing positive? Total probability theorem, right. So let's expand the denominator as probability of positive given D times probability of D plus probability of positive given D complement times the probability of D complement. Great. So you notice that we have this term appearing in the numerator and in part of the denominator. Okay. Now, this term we can just write down using these numbers. 0.95 times P of D. P of D is 0.01. Okay. And in the denominator we have 0.95 times 0.01. Okay. Plus positive given.
0.95.
How did you do that?
By last question.
Right. So remember, conditional probability is a probability. So conditional probability law is a legitimate probability law, and it satisfies normalization. So the probability of positive given D complement is 1 minus the probability of negative given D complement. Why? Because the events positive and negative are complements of each other in this problem. Okay? So then the probability of testing negative given D complement is 0.95. So the probability of testing positive given D complement is 0.05. Yeah? 0.05 times probability of not having the disease, and this is the large number, 0.99. So if you look at this expression, before you compute anything, what do you see? You see that this is close to 1, and this is close to 0. Okay? So this term is what essentially makes this this term is essentially what makes this conditional probability of having the disease, given that you tested positive, small, because it makes the denominator grow. Okay, so if you compute this, let me see. The denominator evaluates to 0.059. Okay, and the numerator evaluates to 0.0095. Okay. What is the result? Let's compute the result. Let me try to compute it here. 0.0095 divided by 0.059. About 0.16. Okay? So this is a relief. If you're the person who was randomly tested positive, this is a relief to you. Okay? The actual chances are only 10%. Now, what would you do if you were this person? Go take the test again. Okay? I would like you to, as exercise, compute the probability that you have the disease given you tested twice with different results and with the same results. Okay, so work this out and see how this probability keeps increasing if you repeatedly test positive, and it decreases if you test negative after being tested positive. Okay, do this as an exercise. Okay, any questions? Okay, what makes this a puzzle, let me repeat, is the fact that this is high. Okay, the fact that the randomly selected person does not have the disease is a high number. It's close to 1. Okay, close to 100%. That's why, even if the test is quite accurate and you tested positive, still it doesn't mean that the chances that you have the disease are high. Okay? Any questions? So let's start the topic, new topic of the day. The new topic of the day is independence. Okay. Independence. Well, two events are defined to be independent of each other if the probability of them both happening at the same time is the product of their individual probabilities. So A and B are independent if the probability of A intersection B breaks up into the product P of A times P of B. Okay? You can show that if the probability of A is different from 0 and B being independent implies that the probability of B given A is equal to the probability of B. How would you show this? Let me do this quickly. So, PB given A, we have the definition of conditional probability, which says this is P A intersection B divided by P of A. Okay. And we have the definition of independence, which says that the numerator breaks up into PA times PB. Okay? So since P of A was given to be different from 0, this cancels. And we get P of B given A equals P of B. think of this a little bit. What does this tell you? This tells you that given that A happened, I don't care. B doesn't care. B doesn't have, the probability of B does not change at all. You know, this information that A happened does not change the probability of B occurring. Okay? This is an equivalent definition of independence whenever this event that we're conditioning on, this event A, has probability different from 0. Okay, so what's next? Now, symmetrically, by symmetry, if the probability of B is different from 0, independence of A and B implies the probability of A given B equals probability of A. Okay? So, let's show that if A and B are independent, so are A and B complement. So, in words, what does this mean? This means that if A and B are independent, getting information about the occurrence or non-occurrence of, in this case, B, does not tell us anything about the occurrence of A. Okay? So let's show this. How would you show this? Well, okay, you're asked to show that A and B complement are independent. We're given that A and B are independent. Let's write this properly. We're asked to show that A and B complement being independent are independent if we are given that A and B are independent. Okay. So, in other words, A and B are independent implies that A and B complement are independent. In fact, the implication goes both ways. Okay? So, well, A and B, to show that A and B are independent, we need to check independent. We need to check that the probability of A intersection B complement breaks up into the product of probabilities of A and B complement. So how do we do this? How about break this into, well, use the definition of conditional probability. Probability of B complement given A times probability of A. This is always true. Now, what do you recommend? Again, use the definition of conditional probability. Use the fact that conditional probability is a probability law and write this as 1 minus the probability of B given A times P of A. Right? And now we use the fact that A and B are independent, which is given. This is 1 minus P of B. Because A and B are independent. And probability B given A is nothing but P of A. Okay? And so, if you multiply out, well, rather than multiply out, 1 minus the probability of B is the probability of B complement. So we are done. Any questions? No questions on this? Okay, let's bring this back. Oh. I guess there's a problem with the connection to the computer. Hmm? Try. Okay. I guess it's coming back. Good. All right, so we show this. Here's an interesting one. If A and B are disjoint, meaning they have no elements in common, are they independent? This is sometimes a misconception that people have. If they are disjoint, are they independent? Or are they sometimes independent? They're always dependent, right? Being disjoint is a very strong form of dependence, actually. Being disjoint means if A happens, B cannot happen. Okay? So let's show this. A and B are disjoint. This implies that the probability of A intersection B is always 0. Okay? In general, this is in general not equal to the probability of A times probability of B unless P of A is 0 or P of B is 0. Okay? So this shows us that events that are disjoint are always dependent. Okay? Let's do a few examples which will illustrate all of these.
Hocam,
Yes, please.
dependent olduğunu nasıl gösterdi? Independent olmadığını gösteriyor da.
Dependent means not independent. So once you find a counterexample showing that this is not satisfied, the identity PA intersection B equals P of A times P of B is not satisfied, it's enough to show that they're not independent. In fact, we'll just exercise this by finding counterexamples in the next example. So in the next example, we have two independent roles of a tetrahedral die. So by now we all know what a tetrahedral die is. It's a four-sided die. Okay? Two independent roles means, so two independent roles of a tetrahedral die. Independent roles. This means that the result of the first role does not affect the result of the second role. Okay? So in part A, it says that independent roles implies AJ and AI and BJ are independent for any I and J. AI is defined as the event that the first outcome is I. And Bj is the event that the second outcome is J. Okay? So let's find the probability that the first outcome is I and the second outcome is J. By independence, this is the probability that AI happens times the probability that Bj happens. What is P of AI? It's a fair die. It's a fair four-sided die. So each face has probability 1 over 4. So 1 over 4 times 1 over 4, 1 over 16. Okay? Any problem? Okay, let's do part B. Part B is, now let the event A be the maximum of the two rolls is 2, and event B is the minimum of the two rolls is 2. Okay? Are A and B independent? Well, if the maximum of the two rolls is 2, this seems to give me some information that there is at least 1, 2. And the only case of the minimum to be also 2 is, the second number being also 2. Okay? So these two events don't appear to be independent, although independence can be very counterintuitive. So we should always check. So let's check this. Event A. P of A. P of A is the probability of the outcomes. The maximum is 2. So we need to have 1, 2, or 2, 1, or 2, 2. And the probability is 3 over 16. Okay. P of B, the minimum of the two rolls being 2. Now, how many outcomes are there? The minimum is 2. So we're looking for all ordered pairs 2, 3, 4 into 2, 3, 4. How many are there? 9 of them. 9 over 16. What is the probability of A intersection B? The minimum is 2 and the maximum is 2. There's only one outcome in that.
Hocam niye normal? 5 değil mi? Bir tanesi 2 olacak.
Excuse me?
Falan mı geliyor? Minimum 2 etmiyor.
Oh, you're right. The minimum being 2. This is wrong. Let's do this properly. Sorry. The minimum, I thought we're looking for the probability that the minimum is at least 2. Okay. The minimum is exactly 2. Has the outcomes 2, 3, 3, 2, 4, 2, 2, 4. And 2, 2. Is it right now? Yes. How many outcomes? 5 outcomes. So 5 over 16. Okay. What is the probability of A intersection B? A intersection B is, as you can see from here, just the outcome 2, 2. The probability is 1 over 16. Is it equal to the product of this and this? No. Hence, A and B are not independent. Let me write it down. Not independent. Okay, so our intuition was right. We thought, before solving the problem, well, this event seems to be very related and dependent with this event, and the intuition was proved right. Let's look at the next example. Okay, let A2 be the event that the first roll is 2, and S5 be the event the sum of the two rolls is 5. Okay, do you think these are dependent? The first roll is 2, the sum of the two rolls is 5. Certainly, the sum of the two rolls is a function of the first roll. So one would, without thinking too much, reach the conclusion that in general, the sum of the two rows and the result of the first row are dependent, which is not wrong in general. But in this particular case, when the events are A2 and S5, the first row is 2 and the sum of the two rows is 5, they will, let's check. Okay, let's check. Okay, P of A2. What is it? 1/4. The result of the first row being 2 has probability 1/4. What is the probability of S5? This is the probability of all ordered pairs summing to 5. 1, 4, 4, 1, 2, 3, 3, 2. That's it, right? And the probability is 4/16, which is 1/4. Okay? What is the probability of A2 and S5? The first row is 2, and they add up to 5. It includes just one outcome, which is 2, 3. The probability of that is 1/16. So, but this happens to be equal to P of A2 times P of S5. So by definition of independence, A2 and S5 are independent. Okay, so this shows you that sometimes independence can occur counterintuitively. Okay. On the other hand, for example, if you tried A2 and S6, let's try A2 and S6. What is the probability of S6? The probability of the outcomes summing to 6. What is that? 2, 4, 4, 2, 3, 3. And that is 3/16. What is the probability of S6 and A2? That's 1/16. 1/16, which is so P of A2 times P of S6 is different from P of A2 intersection S6. Okay? So A2 and S6 are dependent. Okay? So this is not ultimately contradicting the intuition that the sum of the two rows of a die depends on the first row. Only that under some situations, for given numbers, the sum of the two rows being a certain number may be independent of the first row being another certain number. Okay, any questions? So the next topic is conditional independence. Sometimes events may be conditionally independent while they are unconditionally dependent. Vice versa, sometimes events that are dependent may become conditional. Sometimes events that are independent may become conditionally dependent. Okay, let's define conditional independence. Okay, A and B are independent, conditional on C, if the probability of A intersection B given C is the probability of A given C times the probability of B given C. To read this, recall that when we condition on C, C is the new universe. So we redefine everything in this new universe. You already know the definition of independence. Probability of A intersection B is P of A times P of B. So write everything with C in the conditioning. Okay? So simple. Every other result and every other theorem, every other rule carries on as long as you keep C in the conditioning. Let's show something that's kind of intuitive. The probability of A given B and C. Okay? If A and B are conditionally independent, conditioned on C, is nothing but probability of A given C. How do we do this? Again, of course, we'll use the definition of conditional probability. Right? So let me pick a marker. P A given B and C. Okay? To do anything with this, we could rewrite this using the definition of conditional probability. This is the probability of A and B and C divided by the probability of B and C. Right? What's next? What do you think we should do? Again, expand the numerator and denominator using the definition of conditional probability. How about we write this as probability A intersection B given C times the probability of C, the numerator, divided by probability of B given C times the probability of C. How about that? But if the probability of C is different from 0, P of C cancels. What else do we know? We know that A and B are conditionally independent given C. So this breaks up into probability A given C times the probability of B given C divided by the probability of B given C. But the probability of B given C is different from 0, so these terms cancel, and we end up with the probability of A given C. Okay? Any questions? So if A and B are independent conditioned on C, then if you are further given B, this does not add any information. Because if you're given C, A and B are independent, they do not carry any information about each other. But things can change if you drop C from the conditioning. And let's give examples on that in the next hour.